This is chapter 4 in ADS. So what I'm going to do is I'm going to make a new workspace and call it chapter 4. See. Okay, and as for the technology file, I am going to select demo kit, right? Say okay. And as usual, set up layout technology immediately after creating the library and say create workspace. Now in this session, I am going to slightly expand upon AC simulations followed by harmonic balance. And what these are, so what's a harmonic balance? Okay, so what we do is a circuit is a transfer function, and a signal is the input signal is applied to that transfer function, resulting in an output signal. So basically we are convolving the input with the transfer function to give the output, right? Now you can create you can assume that circuit and signal, they are indistinguishable. That is, the transfer function is also a signal, right? So basically you can handle nonlinear components. So for example, if I have a switch which turns on and off, so that's like R on and R off is a square wave, and then I can express this square wave as a Fourier expansion, right? And then I have two signals. Okay, one input signal is applied to that switch, for example, right? So the two signals are convolved to result in an output. So we can do nonlinear simulations this way. But what we are actually doing, we are solving a circuit, okay, for a certain fundamental frequency and its harmonics, right? And then we are combining the results to output. Now how come it handles nonlinearity, right? So basically the input is a signal which has a Fourier expansion, and transfer function is also a Fourier expansion, right? So convolving the two signals, okay, which if we go fundamental wise, fundamental, second harmonic, and all other harmonics, right, then it would be like a linear system, right? So we are solving a linear system for a given frequency component, and then we are combining them. So because the principle of superposition will work here, because we are doing a linear approximation for linear for that frequency, right? So we will be able to combine the output to result in the final nonlinear output, right? So this is how harmonic balance works. So that's what we are going to do. Now one thing to note here is all these frequency components which you feed in as an input, right, their phase relationships between them is, if it is not specified, right, then the solution can have multiple results. So basically the solution in harmonic balance is not unique, because you can change it with the relative phases between various harmonics, right? So in this case, circuits which are in steady states, right, like for example a power amplifier, for example, it can be analyzed, but you cannot analyze a VCO, for example. Why? Because VCO frequencies build up, so it is non-stationary, right? So in this case you cannot solve this in harmonic balance. You can solve this in transient, because transient is a time domain, so it can handle the variation with time, while you can also do a time stepped harmonic balance, which is envelope, right? But you cannot handle a VCO in harmonic balance, right? So these things you have to be clear, where you can use harmonic balance and where you cannot use harmonic balance. Okay, so let's get started. Okay, so I will refer back to my presentation here. So before that, I'll show you how do you copy designs between the workspaces. So for example, this chapter 4 in ADS is a separate project, and I know my design is in chapter 2, right? So what I can do is I can go to manage libraries, and then I can add a library definition file, and in this case I can go to a folder which is chapter 2 in ADS, right? So that's chapter 2 in ADS, and I will take its lib.def and say open. Okay, so this warning you will see don't show again. Say okay and say close. So once you do that, these are from your different workspace library, right? So these are not from chapter 4, they are from chapter 2, right? Okay, so you can see what is from chapter 4 and what is from chapter 2, right? So if you go to library view, you can see that, right? So here, if I look at the S parameter, I wanted to tell you that you see you do not have the data display windows here. You are just seeing the designs. Okay, so you might have to externally copy the data display window. Okay, so this is finally what we had in chapter 2, where we tune this response, right? So I can copy this, right? I can copy this into chapter 4. So I can have to say right click and say copy cell, and just like copy cell, I can say it is still, you know, SP characteristics, but then I'm going to choose a library, okay, where I want to keep it. So I will keep it in chapter 4 library and say okay. So now if you see the view, so this one belongs to chapter 4 library, while this one belongs to chapter 2 library. So once you have copied this, right, you can basically go back and detach your attached workspace. So you can go to manage libraries, you can choose this one and say remove and say yes. Now I have copied this over here. Now this is independent here, correct? So this is how you copy between the workspaces. Now one more thing I want to tell you is I want you to make a symbol for this, right? Like in chapter 3 I made a symbol. So I'm going to quickly make a symbol for this. So I'm going to say file, save as. So I would say SS, small signal gain block, right? So SS gain, and I would say okay. So now I have another schematic called SS gain, and here I can throw out everything which is, you know, the include file and stuff like this, right? I can even remove the grounds, I can remove terminations, right? I can remove these terminations here. I can remove the biases also, because the biases will not be applied at this level. So I can even remove the probe if I want. Okay, so now this circuit which is left, I can add pins. So I can add P in, I can add P out, I can add ground, okay, I can add VDD, VD, and this, to remind me, it is a 4 volt. I am going to say this is a 4 volt. And then I can say VG, and to remind me that this is minus 0.8, what is it, 0.85, right? So I can put here VG. For a minus, I will put a underscore, a 0 underscore 85. So that will remind me that this is a biased at that. Okay, so now that we have created this, okay, we are going to make a symbol for this. So I can say save, close it, and then I say new symbol for this, create symbol, and say okay. Now very quickly I am going to give it a symbol. So okay, so that's the symbol, and I'm going to have P in, P out. Ground, and I can have the supply voltage and the gate bias. Okay, so I'm done with this. So this is my symbol for the PA, the LNA or whatever you call the gain stage, which is tuned at small signal, and I can say close. Okay, so now if I want to use that, okay, so let's set up one more AC simulations. So and this time I'm going to compute noise figure from AC simulations. So let me just show you uh, a presentation before we proceed so that you know what we are doing. Okay. Okay, so we are talking about design hierarchy. Okay, what's the use of design hierarchy? Okay, so a design can be split up into sub-designs or sub-networks. A complex design may result from integration of smaller designs. That's what we do. Okay, merit of such design philosophy is that each sub-design can be perfected separately, right? Then the sub designs have standard interfaces, right? So for example, I can do two designs which have same interface, and I can swap whichever design I want to use. That means that their interfaces should be standard, so allow me to swap. Then the sub designs can easily be replaced by just a click. You don't have to change the symbol and stuff like that, so I'll show you that. Okay, internals of a sub design are not significant. So when you are constructing a bigger circuit, there is a form of abstraction, right? So you are working with the functionality, not with the details of the circuit. So that's what I mean to say, that the internals of sub designs are not significant, I won't say, but I would say they are hidden. This is referred to as encapsulation or abstraction. Okay, rules of abstraction. Standard interface of sub design, okay, is a symbol, right? So basically, if you want to interface your sub design to a higher level of design, you have to have a symbol for it. And symbol is nothing but another view of a cell, and symbol has got pins so that you can connect the circuit in a bigger circuit, right? Okay, and the symbol pins have to have one-to-one correspondence with the schematic pins, right? You cannot just have different numbering of pins and different names and then it'll work. Okay, so the symbol pins have to correspond to the pins in the schematic. Okay, uh, and then the pins are case sensitive, their names and their numbers are also basically unique. Okay, you cannot just change the numbers. Okay, symbols can pass arguments, so these are called design variables. So later I will show you what are design variables. Okay, so make a copy of it. So we did a copy just like that. Then we removed all the stuff which was unnecessary, then added the pins, right? So that's what we did. Okay, so next what did we do? Creating symbol view. So we created a view for the symbol. Okay, so we had a standard symbol, then we transformed it into another symbol. Okay, so now we have a schematic with a symbol. Okay, now to use the symbols, I'm going to drag and drop from the main window, right? So if you make a new schematic, let's say I want to do a test, then I can basically create a schematic and draw the symbol from the main window. Okay, AC simulations. So we have done AC simulations with the op-amp. Now we are going to see how we can use with the RF block. Okay, so we know what AC simulations are and what for they are used. So we are going to do AC test LNA. Okay, so we are going to have this time a AC, and we are going to do a frequency domain source here, right? This is not AC source, it's a frequency domain source. Okay, so we are going to specify a single point frequency. Okay, so we are basically not doing a frequency sweep as we do for the stability analysis. Okay, we are going to analyze this for a certain frequency, and we are putting in the sources frequency domain, and we are going to use a PAC, sorry. Okay, naming the nodes. So we can name the nodes by using this button at the top, and then we can give it a name, and then we can click on the wire where we want to name it. So once you click it, the wire takes that name. Same thing we can do with the Vout, and click on the wire and it will have the name. Then we can just close it. Okay, so to remove the names, you can just again click on the name and then have it empty. Instead of V in, V out, you can have it blank, and then when you click on the wire, that the name would be gone. Alternatively, you can select the name and press delete. So that will remove the name of the wire. Okay, small signal simulation AC. We'll go to noise and we'll say calculate noise, and we will select the pins where we want to compute noise. We want to do it for V out and V in. Okay, data display window will open automatically once the simulation are done. Okay, so we are going to put out V out, add time domain signal, and then we are going to put V in, again the time domain signal, and then we are going to have this. So this is coming from AC simulation. Okay, so next we can write some equations to look at small signal gain. Okay, so this will be 20 log 10 of magnitude of V out divided by magnitude of V in. That will be the gain in dB. Then you can also do a phase. Okay, then you can also do a gain offered to the noise, right? And then the noise figure would be the gain offered to the noise minus the gain offered to the signal. So that's how the noise factor is noise figure is defined. Okay, so that's how we will do this. And we know what is AC simulation, right? We can change the power levels, and you will notice that the supply was 4 volts, but then the V out swings to 12 volts. That's just to prove that it is linearized and restrictions of the supply voltage are no longer there. So that's what a AC simulation is. So let's go ahead and do this, right? Let me see if I'm recording. Yeah. So I'm going to go here. I've already made a symbol for this, and then I'm going to say new, file new, and say schematic, and I will say AC test. So I'm going to do AC test on a LNA. Okay, now to place the sub design, I'll go to the main window, and from here I can drag, and when I release the button, it's going to come up with the symbol for this. So all I need to do is connect the supplies. Okay, so F5 would move the text. Okay, so I'm going to sources frequency domain, and I have VDC, which is 4 volts, and VGS, which is minus 0.85. So this one is 4, and this one is minus 0.85. Right. So we have biased this. Now if we want, we can put in the currents here. Okay, so the currents drawn from the DC supply. So I can say go to probe components. Okay, and here I can mirror this because I want this arrow should be pointing towards the anticipated direction of flow of current. So I am going to mirror this. So let me just expand this. So that's the mirror. Replace it here. Okay, and over here I can say this is the IDS current. Okay, and then I can put in the termination at the load. So in this case I can choose a lump component, and I can choose this as my load. Right, and I can choose the source from the sources frequency domain, PAC. Okay, this is different from P1 tone, which is used for harmonic balance. This is being used for not for harmonic balance, this is being used for AC simulations. Okay, and then I can name the nodes. So this is going to be my V in node, and this is going to be my V out node. Okay, so now that I have done this, I have biased it, terminated it, named the nodes. All I need is an include file now. So I will include the include file over here. Okay, next thing is I need a controller. Okay, so I'll go to simulation AC, and I'll put a AC controller here. Right, and I'm going to do a single frequency simulation. So that's around 7 gigahertz, right? And if you want to display that, you can go to display, remove this, and put in frequency. I'm not sweeping the frequency here. Okay, and also in the controller I can go to noise and say calculate noise, and here I can add V out and I can add V in. So I'm going to compute noise at these two pins. Say OK. So I'm ready for AC simulations. So I can just hit. So I can do one more thing. I am going to put here RF power. So I'm going to put a variable here and call this variable as RF power. And this RF power, I want to put star with 0 as a default value. So here I'm going to put RF power. correct? So move the text over here. Okay, so this is the schematic, and if I hit simulate, okay, let's see what it's saying. Okay, don't worry about this warning. Okay, so now I can put in two waveforms. One is the V out, and I want to put a time domain signal. So that's my output voltage, right? So hang on a second. And then the corresponding V in is over here, correct? Now I want to see what happens when I hit it with more power. Okay, so the transistor is linearized, but let me see what happened with power. I want to put in some more quantities. First of all, I want to put in gain in dB, so which will be equal to 20 uh, 20 log 10, 20 into log 10 of V out into conjugate of I out. So in this case, if I haven't put I out, I would have to put it there, dot I plus 30 for dVm. Oh, oh sorry, why this is not dVm, so that's there. Okay, so I out is not available, so that's red color. Okay, so I have to make I out available. So this is V out over here. I can just put in a probe component over here, and I will have a current go through the probe component, and I will call this as I out. Okay, so once you do that and you hit simulate, okay, so gain is now black. Okay, and I can tabulate the gain value. So I can go to equations, gain in dB. So it says 30 dB. Let me go to the presentation because the gain is not 30 dB. Gain of this is around 10, 11, 12 maybe. So let me see what happened. So we followed almost this. Okay, 20 log 10 of V out divided by magnitude of V out divided by magnitude of V in. Other than that, what did I do? Oh, there is no conjugate here. This will be V out by V in. So I am computing power there. So I'm doing a mistake here. Sorry about that. There's a confusion here. What did I do? Okay, so this is in gain, right? So this will be magnitude of something divided by magnitude of something. So I'm really sorry about goofing up. So this is going to be V out, and this is going to be V in. Okay, so that makes sense. So the gain is around 13.59. Okay, so the gain is around 13.59. What about the phase between input and output? So I can put here phase in degrees is equal to, okay, I can add the phase. So I can just write phase, sorry, phase of V out minus phase of V in. Okay, so that would be the phase in degrees. So let's add that. Okay, so it's 114 degrees. Unlike, you expect 180 degrees in analog blocks, right? So this is because of your tuning, right? So let's now change the input power and see what happens. So I can put here input power on tune, right? So I can go to simulation and I can choose input power, which is RF, and I can give a max value, let's say 20. So I'm going to really compress it, and min value, let's say minus 10. Okay, so now I will look at what happens if I change this. So if I bring it down, the small signal gain remains the same, and the gain would always remain the same because it is not going to compress, and unlike the harmonic balance where you will see the compression. Here, even if it goes above the supply voltage, so right now it's 2 volt swing, you see nothing is happening to gain and phase. Okay, so now it is 8 volts, which is higher than the supply voltage. So this is what AC simulation is doing. It is linearizing your model. It is removing the restriction of the supply. And so the gain remains same as the small signal gain. It's independent of what you are doing as input power. But in real circuits, or let's say in harmonic balance or nonlinear simulation, you will see the change in the phase. You will see the change in the gain as you bring up the power. Okay, so that's that. Now I can close it and say do not update. Okay, what I want to do is I want to write an equation for noise figure. Okay, so gain offered to the signal is this much. Let's see what is the gain offered to the noise. Okay, so here I will call this G noise. G noise dB. Okay, and this is going to be 20 log of V out dot noise. Okay, and V in dot noise. Okay, let's refer to our presentation what we are doing here. Noise figure in dB. Okay, so we have gain noise is 20 log of that, and then we will do the difference of it to find out the noise figure. Okay, so dot noise. Okay, and then the noise figure in dB would be subtraction of the noise offered to the gain offered to the noise to the gain offered to the signal, right? So that's how the noise figure is defined. So I will say noise figure is equal to G dB, gain dB. So gain G noise dB minus gain dB. Correct? So that would be the noise figure. So let's add the noise figure over here. Okay. Okay. So that's 0.326 dB. Okay. So this purpose of this exercise was to show you what AC simulation does, right? AC simulation linearizes the non-linear component and removes the restriction of a supply. So your swings are more than the supply voltage. Okay, so that completes the exercise in AC simulation. Another exercise. Now let's go ahead and set this up for harmonic balance. So let's see what is a harmonic balance. Okay. Okay, so we take a nonlinear circuit component transfer function can be expressed as a series expansion. Excitation signal can be expressed as again a Fourier series expansion, and circuits is solved at fundamental and harmonics over all responses. Okay, and then so this is your gain, which is a transfer function which is expressed as a Fourier series expansion, right? And this is arbitrary input which has a nonlinear input resulting in a nonlinear output, right? So we have got two orders. Okay, one is the order of the signal or the transfer function, right? The other is the order which I'm going to use for mix component, like how much order of mixing do I allow, right? Okay, so there are two things in here. One is the order for the signal, the other one is the order for the mixing, right? Okay, so if you have a P in, which is a Fourier expansion, and then transfer function is like that, we can find out the output. So we are going to just copy this cell, and we are going to put P1 tone here. We are going to do RF power, RF frequency. Then we are going to put a probe component over here, which we have already done. And we have got this, and we are going to put a HB controller here, right? Set up the frequency and the order of mixing here. So order of the signal, not mixing, sorry. And then we are going to put in here what is called a measurement equation to write what is the output power level, right? And we will also see what is the DC power. We will see what is a efficiency. We will see what is the gain. Okay, so we'll write the equations as measurement equations. Later I'll show you. Okay, so measurement equations are different from the equations we have written in the data display window. Measurement equations are written on the schematic itself, right? So once you perform the simulation, you are going to plot it. So if I plot P out in dBm, I am looking at the spectrum. I'm looking at the fundamental, and I'm looking at the harmonics, and the efficiency I'm looking at, right? So we can compute the efficiency, right? So the efficiency, power rated efficiency, is P out divided by P in plus PDC into 100. Okay. Okay, so we can perform the sweep in one of the sweeps in the controller. Then if you want, we can perform another sweep in the another sweep I can perform inside the parameter sweep. So I can plot gain versus output power, gain versus input power. Usually in PAs you are supposed to see gain versus output power, not the gain versus input power, because that makes more sense, right? Because usually you compute output efficiency, you can compute a PAE at a certain output power, not the input power, right? Okay, so we are looking at large signal as parameter, gain compression and other stuff. We will look at accelerometer in a separate session. Okay, so we are going to do a harmonic balance simulation of the same stage, and then we are going to plot the sweep, output sweep versus the input power, right? Okay, so let's do that. Okay, so we have already covered transient simulation earlier with the help of a, you know, when we did a slew rate for op amp, right? So you can also look at another example. Okay, so let's go ahead and do this. So what I'm going to do is I'm going to take test AC and I'm going to copy cell, and this one I will call HP, harmonic balance. Okay, so I'm going to go here. First of all, everything remains the same. Excuse me. I'm going to remove the tune from this, and I'm going to replace this with P1 tone. So go to sources, frequency domain, and look for P1 tone. Now if you want to do two tone, I'll show you how to do two tone simulation, and then I will show you how to do ACPR simulation in envelope, and then I'll show you what is a load pull. So this is coming in the subsequent sessions. So I can put in another variable here. I'll call it RF frequency. Say add, and I'll give it a default value, let's say as 7. If I want, I can put gigahertz here itself, right? Or I'll leave it, doesn't matter. Okay, so this is a pure number, mind it, right? So if this is a pure number, then you have to have a unit here. So this is RF frequency. If you put unit twice, twice of giga, twice units as giga, then it will be 10 raised to 18, right? So you do not want that. And here I'll put RF power. Okay, so we are all done with this. All we want to know is write some measurement equations. So if you go to so I will not do AC simulation. I will go to simulation harmonic balance, correct? And here I can put the frequency as RF FREQ. RF. Okay, in gigahertz, order is 5. So I just want to tell you, this is the order for the signal, and this is the mixing order, right? Okay, so the mixing order is 4 here. Okay, fine. So here I can sweep RF power. RF power. And I can sweep from -20 to, let's say, +8 or something. Okay, so now I'm ready to write some measurement equations. So here in the same simulation controller, you will find measurement equations. Okay, so a little bit about parsing here. I can say, so I'll just open this. Okay, so I can do it this way, or I can have a standard representation. So I can put here a name, which is P out in, so I want P out, right? So P out will be equal to half times of real of V out into complex conjugate of I out. V out into conjugate of something, which is going to be I out dot I. Dot I basically is, because this is not an array, this is a structure, so you have a dereferencing over here. Okay, so that's going to be your output power. Then output power in dBm will be equal to 10 log 10 of 10 log 10 of T out. Now these are going to be all the mixed components, right? So we have to do the proper indexing, right? And similarly, I can have a PDC. DC power would be equal to VDC, which is 4 volts, multiplied by the current drawn, and the current drawn here is IDS. Right? And then it will be IDS dot I, and then I'm going to use the 0 index because this is the DC current drawn. Okay, say add. Okay, you can refer to this also. Okay, here are the equations. Real of this into this, IDS dot I into 4. So we are doing a real because of course it will be a complex number, right? So okay, so let's change this to real of this. You can do a magnitude if you want. Okay, so that's there. So now gain in dB is going to be P out dBm, P out dBm, and it is going to be the fundamental component for which I'm looking for gain minus RF power. Okay, because RF power is in dB only, right? So we'll say add. So that's the gain. And what about the PAE? Okay, so I can say PAE, and this will be equal to P out divided by P in plus PDC. So I'll look at P out at the fundamental divided by something which is going to be P in, which is going to be RF power, plus PDC plus the DC power into 100. So that is going to be PAE, power rated efficiency. Okay, so that's done, and I can hit simulate. Okay, so if there are warnings regarding unable to resolve, you see this PAE is equal to, so there is nothing called RF power, right? So I have to change it. Okay, so this is called RFPWR. Right, and rerun the simulation. Okay, this time I don't have that warning. Okay, that means that PA is computed. So now I can plot gain in dB. Oh, I have a negative value. Why is that? How real of V out into conjugate of I out is P out. Okay, so we should know how to debug that also. I have another way of doing this. I can put here V out in dBm. Okay, so the gain is 13. So this is correct. So this is output power, right? So the output power is correct. So let me just plot here. I don't know what happened to the gain, so let's figure out. So I have output power in dBm, and what I'm going to do is I'm going to plot the fundamental of it. So that computation is wrong, because here V out in dBm is correct, right? So let's see what happened here. Okay, so that's the mistake. To convert this to dBm, I will have to add 30 to it. Okay, so it will be 10 log 10 of V of P out plus 30. So it's in dBm, right? Okay, so now these two figures are the same, right? Okay, so now that computation is correct. So now I'll be able to put gain here. So that's the gain. I can put the gain on the right hand side axis. Okay, so the gain is going through a certain compression. Okay, so this is a single tone. So I'm starting with the gain of 11.97. Right. So I'm starting with a gain of 11.97. So I'll put a marker here. So that's a gain of 11.97. So I'll put another marker, which at 1 dB compression. Okay, so 11.97. So I have to go to 10.97. 9197, roughly here. So at my input of 8 dBm, I have output of 18 point something, right? So that's basically your versus input power. And here I can put gain versus output power if I want. So I can put gain, I can put gain at versus P out in dBm, and here I have to look at the fundamental. Okay, so this figure has more meaning than the other figure, because here we are plotting with respect to the output power. Okay, and I can plot efficiency versus output power. Again, I have to look versus fundamental component of it. So fundamental output power. Okay, so this number is not making any sense. Okay, so let's see what happened to my efficiency numbers. P out 1 divided by RF power plus PDC. What happened to the DC power? DC power is 4 times of IDS times of I0. So let's put IDS I0 here. Let's see what is happening to the current. IDC, IDS, IDS. I want to look at the DC component. So that's the DC component, and I'll put it on the right hand side axis, and I can insert a new right hand side axis. Plot option, right axis, add right axis, call it new axis. It's okay. Then I can go here, plot versus new axis. Okay, so the current, quiescent current, the quiescent current to start with was 37 milliamps, and as you hit it with power, the quiescent current moves up, right? Almost to 47, 10 milliamps up, right? Now, what happened to my computation for DC, PDC? So, what happened to PDC? Again, I'll put this versus new axis. Okay, so this answer is in milliwatts, right? Or in watts, right? So this answer is in watts. So over here I have 180 milliwatts. 188 milliwatts. And I'm delivering. So what's wrong with P out at this point? So let's look at P out also. What? Oh, because P out is versus frequency. So let's look at fundamental. And I'll put it against the new axis. Okay, so the P out is smaller than that. So here I'm putting out 78 milliwatts, and with the input power of 188 milliwatts, DC power of 188. Okay, so the problem in computation is over here. This RF power is in dBm. Okay, so this has to be in, not in dBm, this has to be in, so I'll put here a new this thing which says P in, and P in will be dBm to watts. dBm to watts. dBm to watts. So I'm converting the RF power from dBm to watts. RF power. Okay, so this is converting RF power into dBm to watts, and then here I should use P in plus PDC. So this is how you debug. Okay, apply. So I have to run this again. Okay, so now I can put here efficiency, that's gain, efficiency versus the output power, and here the output power is going to be the fundamental. Okay, and I'll put this on the right hand side axis. Okay, so at 1 dB compression point I have almost 40% efficiency, right? You see here? So that's the 1 dB compression point. I have 40% efficiency. Simple, right? And so what it says that when you hit the transistor with a certain power, then it's DC conditions, the biasing conditions would change. That's what this curve shows, that IDS goes up, right? Now in case of FETs, which are voltage mode devices, what do I mean by voltage mode devices? Because it is a voltage controlled current source. Okay, so this, the FET cannot be driven with a current input. It's only the voltage swing which is driving the output. and then this is with respect to certain quiescent current, and quiescent current is very much restricted because the current gain is going to be infinite, right? So basically the quiescent current is setting up the output power in case of a FET. So this is the basic difference between FET and a HBT or a BJT. In BJT you can put the input power for driving the device, right? And so you are causing a voltage swing on the input as well as the current swing, and both are being amplified. The current swing is amplified by beta, while the voltage swing basically is your GM times of RO. Okay, that will be giving you the gain, right, times of input voltage. So the HBT is a true power device, while the FAT is not a true power device. So you will see that this IDC, when you hit it with power, it can hardly go 2 to 3 times of the quiescent. Okay, so it can only go 2 to 3 times of the quiescent current. So that's your current, sorry. Okay, it cannot go more than that for a FAT. So even if you increase the size of a transistor FAT, that will not work if you keep the current density as fixed. If you keep the currents fixed, you have to keep the current density fixed, or you have to bias it up. Okay, then only you can get power out of a FAT. You cannot just increase the size of the FAT and say that, oh, I'm maintaining the same quiescent current and I'm going to get the power go up. This happens in a HBT, not in FAT. So this you should know when you are a designer for PA. Okay, so we have done harmonic balance simulation here. We have put here the measurement equations. So let's see, have we done everything? Okay, so we did this, we set all this up, we wrote the equation and we plotted it. Okay, so output spectrum I have to plot. Okay, so I'll plot the output spectrum, don't worry about that. Okay, we did the sweep. Okay, one more thing I will do is the frequency sweep. Okay, so let's just look at that. So we will see another form of mixed mode harmonic balance simulation later on. Okay, so harmonic balance can be set up in a number of ways. So let's put it aside. So let's bring in what we have left out. So what we have left out is the output spectrum. So I can just plot P out dBm, and okay, so here I want to look at all the components for a given value. So what I'll suggest you to do is, if you put a marker here, right, and its independent will be the output power. Okay, so not over here. Let's put a marker over here, which is M1. So let's find out what is the index of that M1. Okay, so I will say N is equal to find index, and it's a function, and for that I'll put the series here. Okay, so series here is going to be RF power, let's say RF power, comma, and the independent of M1 is RF power, independent of M1. That's your RF power, am I right? Okay, so let's look at the index value. So in the table I'm going to add the index value. So let's put here a table, and let's put here index value. Equations, that's the index. So right now it's an index of 0. Okay, so if I go up, so it goes index 1, 2, 3, 4. So this is versus power sweep, right? So I can plot at that particular index. So here in P out dBm, you can go here and look at the variable info. So in this case, P out dBm is going to be power sweep versus frequency. So I want to have all frequency components for a given power sweep component, which is n. So over here, n comma everything of the frequency. Okay, and here let's zoom in this thing, and I want to put the trace as spectral trace. Okay, so at n equal to 18, okay, at n equal to 18, the output power is 9. Okay, so n equal to 18, the input power is -2, and output power is 9.9. So that's around 11 point something as a gain, right? Now if I change this, right, so I can see the harmonics to go down, and then I can see harmonics go up as I compress it, right? Okay, so this is about the spectrum. The other thing I want to do is, so I'll get rid of this spectrum stuff, because if I do a frequency sweep, then it will not know the index. Okay, so another thing is I can do a frequency sweep. So I can go here into parameter sweep, and here I can sweep the frequency RF FREQ, and mind you that the frequency is a pure number here, right? So I can go from, let's say, 5.5 to, we have it up to 8.5, right? So we'll look at up to 7.5, right? And let's say we have a step size of 1, 6.5, 7.6. So there are 3 frequency points. Okay, and the inner simulation is in HB1, which is the power sweep. Okay, so it will do the power sweep 3 times for 3 different frequencies, right? So instead of 1 curve, you will see 3 curves over here, right? So I'm going to hit simulate. Okay, so now you see 3 curves for PAE and 3 curves for your output power. Now you see what happened at 7.5. The efficiency fell down to 20, while the efficiency over here is almost greater than 30. So there are 3 curves now. So now this is also a part of your tuning now. So under large signal, you want to have this gain variation to be smaller, right? Okay, and then you don't want the efficiency to be so much spread also, right? So that you can do with the matching, right? So let's see what variations will you come across. So let me just write it down as a text note. So you are going to look at across power. Then you are also going to look at across frequency. And then you are also going to look at across supply. Then you are also going to look at across process. Okay, then you are also going to look across temperature, across ambient temp. Okay, so as a designer, okay, it's not just, it works at one frequency and you are done. As a designer, when you fabricate it and take it to a product, okay, you have to see across power if it is performing, across frequency it's performing, across supply it's performing, across process variations it is performing, across ambient temperature it is performing, right? So the design is not a bookish, childish design. which most of the graduates do in their university, right? I've seen PhDs also doing over a year. They are just doing one frequency or maybe a frequency, but then they are not looking across process, across ambient temperature and other things. So that's not what you are supposed to do. You are supposed to see it across all these corners, right, to have a successful PA design. Okay, so I am going to stop here on the harmonic balance. Let's see if I was recording or talking to myself. Okay, I was recording. So in this we have looked at the harmonic balance simulation. Then what we will do is we will look at the envelope simulation, which is a time stepped harmonic balance, and I'll explain you why we use envelope simulation in the next session. Thanks a lot. Thank you.